Bills backwards.
Yeah, Bills.
And then like, that's how they get yelled at.
Okay, we're going to go ahead and do a problem that involves something where gases are involved and we have some different pressures. Okay, and it's Gibbs's free energy. When you calculate it, we did some of those calculations yesterday. And so if Gibbs's free energy is negative, then that means it's what? Spontaneous. In all situations. And then if it's positive, it's non-spontaneous, right? Okay. So I didn't give you very many problems to do. And so we're going to look at one. Now we looked at one that would be where it's at different temperatures. We said, if the temperature goes down, how that might affect your overall value. Temperature goes up when we have a positive or negative entropy. Okay? So what we're going to do one is, some of this, since it's chapter 17, we would have probably already went through what Q and how to find Q. It's called a reaction quotient. Okay? And you do that in reversible reactions. And so we would have already went through that, but I need to show you that so that you understand what Q is. We know what temperature is. This R value is going to be the 8.31. So I know we used that constant when we were doing it, but this R value is associated with work. And the R value is associated when you deal with work. If you did any problems where that was part of it, that would be 8.31. So just remember that. That's 8.31. Okay? All right. Also, I know Jared's probably listening to this, so you guys want to say hi, Jared?
Hi, Jared!
Wish we were here. You're sick, or at least that's what you say you are, so we're going to go with that.
He's skipping.
All right?
He's lazy.
He's skipping?
He's skipping water hydration part.
Yeah.
You missed out on pumpkin pie today,
Pumpkin
buddy.
pie, man. Forget it. He's saving for you.
I can see him with this laughing right now.
Is there pie? He's literally sitting
Is your pumpkin and pumpkin pie? No, I didn't say that, Jared. That was okay. We're just going to do one of these problems, and then I'll have you do a couple on your own and add it to the 3 that you did. I don't know what we'll do tomorrow. I don't know if I will do anything tomorrow.
moldy.
I could pull out the whack-a-mole. We have a whack-a-mole.
Yeah. You better be here tomorrow, Jared.
Or we could have bedroom.
We can make s'mores. I do have.
Do you want to drink your barbecue in class tomorrow?
Sure. Yeah, that's 12 more.
Yes! 12 more. All day celebration.
I figured it's like 12 of those little packets, like a Dairy Queen. Maybe 12 of those.
That's easy.
Just don't let Jared have anything spicy, or he won't be.
Man,
Okay.
what's going on next today?
So this is a delta G, and a lot of times you'll be given the delta G already for the reaction. So it'd be kind of like when we give you enthalpy for a reaction, you'll be given the delta G. But what will happen, and engineers, chemical engineers, I know that they do this like at some of the plants in town here. They do reactions to get the most product in conditions where they add pressure or they take pressure away, they add temperature or they take temperature away, because what it does is it drives the reaction toward the product side. So, and they want to do it with as little energy that's needed as possible. So if you can do a reaction that needs less energy. That means less money that you'd have to deal with. And it's a balancing act, you know. If you increase the pressure of a gas, then that means you've got a pump that's running that's going to increase the pressure of that gas. And that takes electricity to do that. That takes energy to do that. So they have to weigh the pluses and cons. And there's lots and lots of variables that's involved. So if you're going to be a chemical engineer, that might be one area that you would look at. And you're always looking at reactions and if you're getting the most bang for your buck. And that's part of it. That's not all of it, but that's some of it. So what is a reaction quotient? I made a fictitious reaction here. 2A plus B 2C gives you 2AB plus C, and they're all gases. Okay? We would need to know all the partial pressures for all those gases. So now if it's a solid, you don't include it in this, and our example will show that. So if it's a solid or liquid, it's not included in this calculation because it doesn't have a pressure. A solid doesn't have a pressure. A liquid doesn't have a pressure in the whole system. It's only the gases that do. So that's all we're going to look at are the gases. So if we're doing this, what happens is this coefficient out in front will eventually be either squared or cubed. If there's not one in front, then you just leave it by itself. So you'll know what that is here in a second when we do this example. So what we're going to do is we're going to take products over reactants. So here's our products. So we're going to take the partial pressure. I'm going to put it as P. So we would be given the partial pressure of AB. So that would be P of AB, identifying it, and then that would be squared. So the pressure of it, so if it was 1 atmosphere, it would be 1, right? If it was 2 atmospheres partial pressure for AB, it'd be 4, right? For that part. Then you would multiply that by the C, and it's not squared because we only have one of them. So it'd be 8, that should be P of C. Okay? Hopefully I get messed up and then I don't erase very good with this. So then we go, it's over the reactants. So what would be underneath? What would I do?
The partial pressure of A.
Partial pressure of A squared
times the partial pressure of
yeah.
B2C.
B2C. Partial pressure of B. Actual numbers work better. I understand that. So what we'll do is we'll take this squared times this divided by the product's pressures squared. I know that's a lot of gibberish there, but in our example you'll kind of see. It's not that hard to figure out when we do our example. So here's our example that we do. A real life example that we're going to do. So we're going to calculate the delta G at different pressures. Okay? So that's what we're going to do. And so here's the reaction. The reaction is CO, carbon monoxide gas, plus H2, and that would be a gas, is going to produce methanol, CH3OH. And that's a liquid. Okay? So I think it's balanced, right?
Yeah.
Mm-hmm. Okay? Now I'm going to give you some values. The pressure, partial pressure of CO2 is equal to, or CO, not CO2, but CO, is equal to 5 atmospheres. And the partial pressure of H2 is equal to 3 atmospheres. Okay? And the conditions this is at, it's at 25 degrees Celsius. Is what it is. Okay? So, giving you an equation, and the equation I already put down, but I'm going to put it down over here, is delta G is equal to change in G plus RT and natural log of Q. Okay, let me rewrite that because I run out of room and I try to shorten it. I can't write very good like this. So do it again. Cool. So, change of Gibbs at free energy equals change of G, standard state, plus RT times the natural log of Q. There we go. Okay. So on this reaction, it says that the actual reaction has a Gibbs's free energy that is calculated is going to be a negative 29 kilojoules per mole. So this reaction, the delta G for that reaction, if we go through and calculate everything, and you could do that, would be a negative 29 kilojoules. Okay, for that reaction. Okay, so then we're going to go ahead and do our calculations. So before we do that, well, we can plug it into the equation. So we're going to go ahead and say delta G is equal to a negative 29 kilojoules plus, what did we say R was going to be? 8.31 times the temperature. What's the temperature? 298. Times, now I'm gonna run out of room, so let's set this up and then we can just plug in the natural log of our Q. We'll plug our Q in there. So let's do it. So it's our products over our reactants, right? So this is L, and so it doesn't go in there.
Zero is zero.
Well, it's not zero. What it's going to be, basically, we're going to put 1 for the top, okay? Because we can't put 0 there because then we won't get a value. So it's going to be 1 over, then the CO, how would we present that? Just 5? 5 atmospheres times what? 3
times
squared. Right? 3 squared. And so that would be 9 times 5, right? 9 times 5 is 45, so 1 over 45. So what would that get us for a value? What is it? Somebody calculate it for me. Okay.
Oh,
What over? 0.0 something?
0.02.
What is it?
0.022222.
2 repeating? Okay. So I want you to guys plug this in your calculator. Now we got everything, all the numbers. I need you to plug it in. So that 0.022 goes in here. So the natural log of 0.022. So let's calculate delta G. So go ahead and get your calculator out and figure that out.
Yeah.
What's natural log again? The log is E?
Yep.
Log base E?
Yeah.
It's just some random number, right?
Yeah, it's a natural number that occurs in nature a lot.
Yay. Hi, Jared. Mr. Garland is gone. Did you guys get like negative 9,400?
Yeah. Negative 9,480.
What's the 5 times?
Yeah, we can't.
Now, the thing I didn't include in this is 8.31 would have units of joules.
8.31 is joules. So you
Yeah.
convert that.
Well, you can do it one way or the other. The
That's what I
book,
was thinking.
the book tends to changes this to joules. So it'd be 29,000. It'd be 29,000 joules. But we could do it either way, it doesn't matter. So this will be a joules, and then so we'll have to divide that by what?
1,000.
1,000. So then we can get it in kilojoules, because this 8.31 will always be in joules, because that's what it's always measured in.
And that's, that 8.31 is up the...
That's the R.
That's R, that's. Yeah.
Okay, so what did we get for a final answer once we plug all that in? Negative what?
38.
Negative 38,451.
Joules.
0.6
You were right,
joules.
you just did
Okay.
subtract. Add the 29.
So the negative, is that total?
Yeah.
Or what'd you get for this part?
Oh, I converted the kilojoules into joules, so I don't know where it is.
I got negative 9,451 joules.
Okay, so this would be minus 29 kilojoules plus, you got a minus
9,451 joules.
Nine-
So 9.451.
okay, 9.451.
Yep.
And that would be joules, no kilojoules. If you plug it in without the 1,000, it'd be 94,510, right? That's right. I mean, that's right. Okay, so then this final answer is a negative 38.5 kilojoules. Okay, listen. Now, the delta G went from a negative 29 to negative 38.5. So what happens that it's even going to favor a more spontaneous reaction because it's a higher negative number. So what happens when you take a look at delta G is more negative, so that's implying that the reaction is more spontaneous at pressures greater than 1 atmosphere. So at what point does it get, at what point do you have to increase the pressure to make this an advantageous reaction to make money off of it? Because this is a fuel. Methanol is a fuel. And so, see, they have to look at pressure. The container it's in, how much pressure can it withhold? How far can you go? I mean, how much pressure you have to put into it. So it's all, a lot of variables involved there. So I know that one problem took a little time to do, but I want you to do a couple of those just so you can see how you've got to take, it's kind of like entropies. The same thing, entropy is in joules, and you got to divide it by 1,000 to get it into kilojoules. So it'll be the same idea. All right. So I'm going to go ahead and add a couple problems to this.
Yes. I was looking for my book. I thought it was it's the G plus
You have to find for the 7 do you not change the G part?
You do. You'll have to calculate it. Those are good. Those are practice problems that you'll have to. You won't be given the delta G. You have to calculate it. So, but once you calculate it once, it'll be for all the problems.
How do you calculate G?
Products minus reactants, and you look them up in the back of the book. You look up delta G, and you do it the same way as enthalpy, and the same way as entropy.
What's the equation again? Change G with the dot plus RT.
Plus RT.
Times natural log of Q.
So change G, look that up.
What page did I say it was? 7?
702.
702.
C.